So, what if an AI could do more than just, chat? What if it could predict the unpredictable? Not just words on a screen, but the actual physics of the world all around us. Well, today, we're going to dive into a totally groundbreaking AI that's learning the super strange, complex, and honestly kind of messy rules of how fluids actually move.
Okay, so let me ask you something. Why is it way easier to predict where a river's going to go than it is to predict how ketchup's going to come out of a bottle? I know, it sounds a little silly, right? But the answer to that question gets to the very heart of a massive challenge in physics and engineering. Because that ketchup, or the paint on your wall, or even a lot of cosmetics, they're all part of this group of materials that are just notoriously difficult to model. And that right there brings us to what we can call the unpredictable flow problem. Seriously, to really get why this new AI is such a big deal, we first have to wrap our heads around why predicting something as simple as ketchup has been such a headache for scientists for so long. The fancy scientific name for this stuff is complex fluids, and what that really means is they're materials whose behavior depends on their history and their internal structure. Just think about it for a second. When you shake a ketchup bottle, you're literally changing its history, right? And that makes it flow differently. It's the same thing when you stir paint. In a very real way, these materials actually remember what's been done to them. And this comparison here really lays it all out. Water, that's a simple fluid. Its viscosity, its thickness, it's always the same. The physics are pretty straightforward. But something like paint, oh, that's a whole different ballgame. Its thickness actually changes depending on how you're moving it. The physics are what scientists call nonlinear and time-dependent, which is basically just a very technical way of saying they are an absolute nightmare to predict.
So you can imagine trying to simulate these things on a computer has been, well, a real struggle. You need a ton of computational power, the calculations take forever, and maybe the worst part, you pretty much have to build a whole new model from scratch for every single different scenario. It's no wonder the whole field of non-Newtonian fluid mechanics has been this super specialized, kind of walled-off area of science. Right, so why has this been such a closed-off field? To get that, and to really see why we desperately needed a new approach, let's take a quick look at the old tools scientists have been working with. Okay, so way back in the 70s, we got these traditional numerical methods. And look, they were powerful, but like we just said, painfully slow. Then fast forward to the 2010s, and we started seeing some early AI models, things called PINs, that's physics-informed neural networks. They were definitely a step up in speed, which was great, but you still had to retrain them for every single new material or different condition. So the bottom line is this. For decades, science has been on the hunt for a solution that's general, flexible, and most importantly, fast. And that is exactly where this new technology comes into play. It's called RheOFormer. Now, this is not just another AI that's, memorized a giant library of simulations. No way. RheOFormer is a totally new kind of generative AI. And its big breakthrough is that it doesn't just copy the data it's seen, it actually learns the fundamental rules of fluid physics. It's almost like teaching an AI to think like a physicist. Okay, so its full name is a bit of a mouthful, the rheological operator transformer. But what's really at its core is an AI model that uses a transformer architecture. And yeah, that's the exact same kind of tech that powers the big language models you probably heard about. It uses that architecture to predict, with incredible accuracy, how these complex fluids are going to change and move over space and time. And listen to this. The researchers themselves are saying this framework is a massive step forward. They're highlighting its potential for things like real-time process control, designing brand new materials, and something called digital rheometry, which is really just a cool way of saying you can run virtual experiments on these fluids way, way faster than ever before. All right, so how on earth does it actually do all this? I mean, how does an AI like RheOFormer even think about a fluid? To answer that, let's peek under the hood at its architecture. It basically breaks down into 3 key steps. First up, you've got the encoder. This part looks at the fluid's current state and uses this amazing mechanism called self-attention to see all the spatial patterns at the exact same time. It's like getting a perfect, complete snapshot. Then, step 2, the decoder comes in and asks the big question. Okay, based on that picture, what's going to happen next at any spot in the fluid? And finally, step 3, the propagator. Now, this is the really slick part. It predicts the future, but it does it by working in this compressed, simplified, latent space, which, as you can guess, saves a huge amount of computer power. So, if you're looking for the secret sauce, this is it. It's this killer combination of two things. First, that self-attention lets it see the whole picture at once, how every single part of the fluid is affecting every other part. And second, it makes its predictions super efficiently in that compressed space. So what you get is a model that's both incredibly thorough and incredibly fast.
Okay, so that's the theory, which all sounds great. But the real question is, does it actually work? Well, you better believe the researchers put RheOFormer through some seriously tough virtual tests to find out. So for their first big test, they simulated what's called a viscoelastic fluid. Just think of something that's both thick like honey, but also springy like rubber. They had it flowing through this narrow channel that suddenly gets 4 times smaller. And let me tell you, this is a classic, notoriously difficult problem in fluid dynamics.
And the comparison here is, well, it's just striking. What you're seeing is the ground truth. That's the perfect exact result you get from a super slow traditional simulation. And then you see RheOFormer's prediction. But here's the kicker. The AI only got to see the first few moments of the flow. And from just that tiny peak, it predicted the entire rest of the simulation with insane accuracy. I mean, look at them. The patterns are practically identical.
Okay, but what happens when you throw something even more complex at it? For their second test, the challenge was to predict the super intricate wake that forms when the fluid has to go around a triangular obstacle. You know, like water flowing around a rock in a stream, but way more complicated.
And again, the results are just stunning. The ground truth simulation shows you all the complex little swirls and eddies, the vortices that actually form. And then you look at RheOFormer's prediction, and it captures those exact same features almost perfectly. This proves it's not just good with simple stuff, it can handle complex shapes and even chaotic behavior.
But honestly, here's what I think is the most mind-blowing part of this whole thing. The model was tested on flow conditions and different types of fluids that it had never, ever seen during its training. And it still got the physics right. This isn't just a party trick of memorizing things. This is true generalization. It didn't just cram for the test, it actually learned the subject. So, what's the big takeaway here? What does all this mean for the future? Well, it's not an exaggeration to say we could be looking at the start of a whole new era for how we understand and engineer with fluids.
So why should you care? What does this mean in the real world? Well, this tech could mean we get new smart materials designed way faster than before. It could let us control manufacturing processes, think 3D printing or even making food, in real time. It speeds up scientific experiments, and maybe most importantly, it makes these incredibly powerful tools available to a whole lot more people.
And that's really the big picture here. This AI is helping to democratize a field that has been super technical and specialized for a long time. By making these simulations fast, flexible, and useful for all sorts of problems, it's putting these amazing tools into the hands of so many more scientists, engineers, and innovators. And all this leaves us with one last, really fascinating thought. For decades, right, we've used computers to just crunch numbers based on the laws of physics that we gave them. But now we have an AI that can actually learn those laws all by itself, even for some of the most complicated systems out there. So it really makes you wonder, doesn't it? What's the next big, complex challenge we should point it at?